Jairam ji ki. We will discuss today about physical analysis of foods. The parameters that we'll talk about today, first specific gravity, which is relative, it is kind of an index. It is actually ratio of densities, and it is to know whether a product will float or sink in water or in any other liquid. We'll talk about density, which is nothing but mass per unit volume. It can be true density, it can be bulk density or tapped density. Talk about surface tension, which is a tension on the surface. It is more important, pertinent for deciding whether a particular liquid will be miscible with water or any other liquid. Viscosity, which is nothing but resistance to flow. That means every material, all material, they have a resistance to flow. They don't want to flow. So that is to do with workability of semi-solids. For example, when we make chocolates, thick semi-solids, so how do they flow and how do we maintain and maneuver their flow? That is the important property, viscosity, which the next term of course is rheology, but not today. We'll talk about viscosity only. Then we'll discuss about moisture, which means the water which is there in the food products in the absorbed form, in adsorbed form, or it is entrapped within the pores very deeply and very strongly. That means almost like chemical bound. Refractive index, that is refraction of light through foods. So various, as we know that all matter, when the light interacts with them, there is a phenomena of one reflection, the other one is refraction. Refraction means when the light moves through the medium, and when it goes from lighter medium to dense medium, the angle of refraction actually lowers down. We'll talk about filled, that is something which is undesirable. It is a critical parameter. It is because of the contaminants, and it is completely unacceptable. We'll discuss about particle size, diameter, distribution of particle size, fractions, different fractions of particle size. We'll also talk about water activity, which is vital for controlling the microbial growth. Say, for example, products like pickles, products like based on sugar syrups. So for their longer shelf life, the water activity is a very important parameter to take advantage of. So we'll go one by one. The first is specific gravity. There are two terms. One is gravity, the density, and the other one is specific gravity. A specific gravity basically is a ratio. It is density of matter divided by density of water. So density of substance, they divided by density of water. I just give you the example of how important it is. Say, for example, you pick up mango from the tree and you just put it in water. You will see that if it is a fresh from the tree mango, it will float. It will float because of the term specific gravity, because we are comparing it with water. Now, if the specific gravity is lower than 1, it will float. But the ripened mango, it is heavier than unripe mango, so it will settle down. The idea is to give you the relevance, the significance of specific gravity. In the plants, in the processing unit, when we design plants or when we design flowing systems, we always take into account what is the specific gravity, so that we know whether the material will float, sink, and to what extent float and what extent sink. Look at the applications of specific gravity. It first of all defines whether a material will float or sink, how much it will float and how much it is sink. You see on the right side, the first figure, different levels of sinking. Then it determines the purity of the substance and determines the quality of food. So if we know the real density, true density of a food, and if you are checking its quality, if it is not as per that, that means the food is impure. So for purity also, it can be parameter. Differentiate different grades of food. If you are comparing, suppose for example, you are buying wheat and you are buying wheat from different markets, then to compare one grade from the other, you can use density as the criteria for knowing the grading. The equipments that you design in the food processing plants, specific gravity is very important, density is very important. Look at the figure which is in the bottom. One particular substance is settled in the bottom. The second one in the middle is completely floating. And the third in the last you see is half floating, half sinking. So if, for example, I just give you the example of a specific gravity of a material 0.8. Suppose there is a solid material which is of specific gravity 0.8. If you put it in water, 80% of it will sink, 20% of it will float. If it is a specific gravity 1, it will not be sinking, it will not be floating, it will be at the same level. But if it is, say, for example, 1.2, the whole material will sink. If it is further less, suppose 0.2, then 20% will sink, 80% will float. So this gives you an idea about what significance specific gravity has. In order to determine the density, the ratio of mass to volume. So you want to know how much is the mass of a unit volume. Now density is one true density. That means there is nothing else is involved, only the mass of the material, mass of the food product that you are checking the density of. But generally, food products are handled in bulk. Say, for example, wheat grains, pulses, all sorts of millets. They are all handled in bulk. When we say bulk, that means the material along with the air which is entrapped. So when you have grain, a container full of grain, along with the grains there is also air. So that is aerated bulk density. But if you tap it, for example, if you press it or you put one sack on the other, then one sack is pressing the other below. So there is a tapping. When you tap, you can fill in the same sack more material. That is called tapped density. So weight per standard volume, and it is compacted weight, the bulk density which is tapped. Tapped bulk density is always more than the aerated bulk density. Now index of how food grains, aerating is there or how loosely they are there, bulk density will depend on porosity, particle size, moisture content and density. Increase with the moisture. If the moisture level is high, then the bulk density will increase. If porosity is low, bulk density will increase. But if it is more porous, the bulk density will go down. And degree of compaction, as I told you, one sack or the other, the bulk density will increase. The flour mills, for example, when they design the flour mills, they always take into account what would be the bulk density of the wheat. So, for example, for determining what will be the yield of the flour mill, milling yield depends on the bulk density of the grains like wheat or pulses or anything. So, true density, which is the density of the matter as such, no any entrapment of air, no air aerated, completely it is only material, that is true density. But if it is aerated, it is bulk density. It is measured first by the pycnometer or by the density bottle. You see it on the right side. But then there are other devices also which are actually also not only for density but also for specific gravity, like lactometer, hydrometer, or in the case of hydrometer, you can have various series of it. It can be meant for alcohol, it can be meant for molasses, it can be it can be designed for any kind of solvent. Lactometer is a type of hydrometer which is actually designed for checking the specific gravity or density of milk. So if the hydrometer, it goes lower the density of the fluid, deeper the float B will sink. You know, you see in the picture below, there is a part A, there is a part B. B is a heavy part. A is a part which is graduated, which will tell you about the level. So when you put this hydrometer into the liquid, it will float or sink. So if it sinks deep, that means the density of the material is lower, and the graduation on A is based on the calibration. It is calibrated as per the requirement. If you are calibrating it for alcohols, then you do it for it becomes alcoholometer. If it is for milk, it is become lactometer. If it is for others, then it is hydrometer designed for that particular liquid. This is another way, Westphal balance, in which you are dipping the, instead of just leaving the hydrometer as such, you are now weighing the amount of water which is displaced by it, and this is another way of doing the relative density and specific gravity. Let's go to the next topic, that is specific heat capacity. What is a specific heat capacity? A specific heat capacity is nothing but the amount of heat required, how much heat you require to raise 1 degree temperature of a substance. So suppose you take water, how much heat is required for raising its temperature by 1 degree? So you can calculate the heat required to raise temperature of a substance by certain amount of degree. If you know by 1 degree, then you can know how much it will require for 40 degree, 50 degree. The unit for this is joule per gram per kg per Kelvin, or calorie per gram per Kelvin. Now heat required generally is by the formula mass of the material, specific heat capacity, and the temperature difference delta T. So Q is equal to M into C into delta T. Now let us take one example. I have 100 gram of water, for example, and specific heat of water, for example, is 1 calorie per gram per Kelvin. So if I take 100 gram of water, and if I want to raise the temperature from 0 degree to 35 degree, okay, or 10 degrees to 45 degree, or 20 degree to 55 degree, that means that delta T is 35. Then I would require 3,500 calories. Here the heat capacity, specific heat capacity of water we have taken, as I told you, is 1 calorie per gram per Kelvin. So we would need 3,500 calories. Let us do one numerical on the same thing. Suppose you have 20 kg of water and you want to heat this water from 10 degrees to 100 degree, and you have a heater, you have an immersion heater, immersion rod, which is of actually 1000 watt. So you have 1000 watt heating rod and you want to heat 20 kg of water from 10 degrees to 100 degrees. You want to find out how much heat is required for this. Remember, specific heat capacity of water, for example, is 4200 joules per kg per Kelvin, or 1 calorie per gram per Kelvin. So this is in joules now we are talking. Now the mass of the water that you have is 20 kg. Initial temperature you have taken is 10 degrees. The final temperature is 100 degrees. So delta T becomes 90 degree. So you want to have an increase of 90 degree of water and you have to give heat. Heating is by 1000 watt rod, which is working at the efficiency of 80%. So only output is 80%. So basically you are getting 800 watt. Okay. So the heat required would be, as I told you, mc into delta T. M is 20 kg, C is equal to 4200 joules per kg per Kelvin, and delta T is 90 degree. So basically we will get about 75,60,000 joules is equal to 75.6 into 10 raised to the power 5 joules per kg per Kelvin would be the heat required. So now you are able to calculate yourself how much heat is required for raising the temperature from 10 degrees to 100 degree of water. Let us take this example, how much time it will require, for example. So time required generally is energy consumed into time divided by output power, how much power output you had given. That was 0.8, I told you 80% was the output. So energy consumed was 75.6 into 10 raised to the power 5 joules is equal to 0.8 into 1000 watt into time. So time comes 9450 seconds. So that means 2 hours 37.5 minutes. So by this, if you have the value of specific heat of any material, food material, and you are designing your processing plant, and you want to design the heating system, then by this specific heat method, you can know beforehand what all you will require, how much time it will take to range from one temperature to another temperature, and what kind of heating arrangements you have to put in place. Let us talk about surface tension. This is a very, very important property, especially of liquids, okay? Now, in the case of liquids, what happens is all the molecules which is there in the liquid form in the body mass, full mass, they are all attracted with each other. Look at this. The molecules inside are attracting each other. The molecule which are above it, they are forces downwards. Below it, they are upward. The forces are getting cancelled. But those which are on the surface, on the top, on the surface, there is no balancing on the top side, because on the top side is air. So the forces which are upward actually are making the layer, water layer or any liquid layer, stretched outside, and that is called the stage of tension. If you want to understand the surface tension, the best way to do is to put a small oil pin on water, and it will not sink. The reason for that is the tension which is there on it. Even though the density of steel is very high comparison to water, normal cases it will sink, but the oil pin that you put it there is able to, the weight of that is compensated by the tension the water has, and it will not sink. This is important from the point of view when you have to mix two liquids. For example, you mix oil with water, ghee with water, they will never mix with each other, because each of them have a tension, and because of that tension they are not miscible. So in order to make them miscible, you are supposed to reduce tension. How do we do it in the food industry? You must have seen on all the processed food, there is a term called emulsifier. You look at the packet, they write all the contents, and then they write food grade emulsifiers. Those emulsifiers reduce the tension. How do you measure the tension? As I told you, there is a tension upward. The top layer of the liquid is stretched. So to measure it, you can easily do it by the capillary rise method. You put a capillary in the liquid as it is shown in this figure. Because of the tension, because of the pressure upward of the liquid will rise in the capillary. How much is the height, up to what height it has risen, and what is the radius of the capillary, you can actually calculate the surface tension by the formula R into H into D into G divided by 2. R is the radius of the capillary, H is the height by which the liquid rises. If it is water, how much water has risen. If it is alcohol, how much alcohol has risen. So you know the height that the liquid has gone up in the capillary. D, which is the density of the liquid, that you know, and the G is the gravity. So multiply all four of them, divide by 2 is the surface tension. You can also do it by the drop method. Now you see, in this one I had explained to you why there is a tension. By tension, the top surface is stretched. What does it mean? That means the drop of any liquid will always be spherical. It will never spread. Suppose you put water on the tile, it will never spread unless there is a reduction of surface tension, unless the tile has got a coating which reduces the tension of water. So if how the spherical the drop is and how big the drop is, that can be the method, that is a principle for doing surface tension by drop method. So what you do is, you have a capillary and let the drop fall down. This is by the stalagmometer, and stalagmometer, from the orifice the liquid is allowed to fall. Now how many drops it is forming? Suppose, for example, you take stalagmometer and you make the milk fall. You put the stopwatch and count the number of drops. Suppose there are 200 drops compared to 100 drops of water. That means the surface tension of is 1/2 of water. If the surface tension is more, there will be more number of drops. Okay, surface tension is less, more number of drops. If it is more, there will be less number of drops. So a liquid showing 200 drops compared to 100 drops of water would have surface tension 1/2 of the water. The other method is torsion balance. In this one, what you have is force needed to detach horizontal ring. What you do basically is you put a ring, horizontal ring on the surface, and you attach it to the platinum wire, and you pull the wire up. the amount of force it requires, that will be the tension. All the surface tensiometers, they are based on this principle. Next property that we are supposed to talk about now is viscosity. As I told you, viscosity is resistance of a liquid to flow. That means there is a frictional effect due to passage of when the material is flowing, there is a top layer and there is a layer below. Okay. So the one layer or the top layer of the fluid, which is above the lower layer, there is a coefficient of viscosity, that is force per unit area, which is maintained a unit difference of velocity between parallel plane of fluid at 1 centimeter apart. Assume that there are two planes, one at 1 centimeter above the other one, then the coefficient of viscosity is force per unit area required to maintain unit difference of velocity. Now the kinematic viscosity is equal to ratio of dynamic viscosity and density of the same temperature. The unit of kinematic viscosity is Stokes and dynamic viscosity is dynes per centimeter, which is there in the poise or centipoise. Method that measures resistance to shear offered by the liquid is used for determining the viscosity. Now, easy relevance of viscosity is, you have honey in the beaker or honey in the vessel. How quickly honey will fall, compare it with how quickly water falls. You know it very well, viscosity of water is much lower than that of honey. So in designing all sorts of flow equipment in the processing plant, you need to have the knowledge of viscosity, which is nothing but resistance of any fluid to flow. You want to push it, it will resist to flow. This is example like, for example, butter. The top graph shows the highest yield. Yield is how much pressure you put to spread the butter on the bread. And you see different kind of, this is rheology, which is different from viscosity. Viscosity is for the pure liquid. Rheology is for the for the systems which are more than one phase. For example, something which is there suspended in water. In the case of butter, for example, it's an emulsion. So water is there and ghee is there together. Then you don't do it by viscosity, you do it by rheology. And yield stress tells you how much resistance it has to flow. In the case of butter, it is very high. In the case of oil, it is very, very low. You see it in this figure. These are the applications, how you mix one into another, two products mixing. Viscosity plays an important role. How they will flow in the pipelines, how you would be able to handle them, like chocolate manufacturing, dough manufacturing. All this is part of knowing their rheology and dependent on viscosity. Let us talk about moisture. The next property that we talk about, moisture. All food products contain moisture. There is no food which does not have moisture. So when you buy it from the market, if you don't know how much is the moisture, then this has no relevance. For example, you buy 10 kg of flour, and if flour contains, for example, 10% moisture, so that means you actually have not bought 10 kg, but you have bought 9 kg plus 1 kg moisture. So this is true for all products you buy it in the market. How much is the moisture you need to know to understand the value of your product. So moisture measurement can be directly, you remove the water which is there and know how much is the weight loss. For that, what you do is you either dry it in oven, you dry it under vacuum, you do it freeze dry under pressure and low temperature, you dry it by distilling, or you do it by Carl Fischer method. But then there are indirect methods. You do it with calibrated, you have an equipment which is calibrated, and there can be number of you can have refractometer, you can have infrared absorption, you can have near infrared, dielectric capacitance, mass spectrometry. All these equipment are already calibrated. So you take your sample, do the analysis and know what this moisture is. So direct method, indirect method. Let's see the direct method. The problem in the case of moisture measurement, please understand, is that if you are not able to remove the moisture properly, then you end up underestimating the moisture. In your efforts to withdraw all the moisture, if you give harsh conditions, then the material can decompose. For example, you raise the temperature for removing the water, and that temperature may damage your food product. So either you underestimate, your estimation is lower than actual moisture, or it is damaging your product, so erroneous results. So to remove the error, you have to be very, very careful what kind of method you use. For example, AOAC method says that your temperature in the oven should be 98 degree to 102 degree at 25 to 100 mm pressure, and you do it for 200 to 600 hours. But if suppose your product is heat sensitive, the same method would be done for 60 to 70 degrees temperature of the oven. So depending on your sample, you will choose. There might be samples where you will, instead of 98 to 102, you may have to do 110 and 120 degree. But then the time will be less and the pressure would be the same. So depending on the product that you are determining moisture in, you have to be very careful about choosing the right method. This is the distillation method. In this one, what you do is you take your sample and you take your sample along with a solvent, okay? Non-polar solvent like mineral oil, which has a boiling point higher than water. So when you start heating the material, then along with that solvent, water will also go, and then you see in this one you have a trap there which collects the water. So this is by distillation, you distill, condense the water which is coming out, and your solvent is falling back in this one. That is almost like reflux boiling, where solvent will fall back, and where you are collecting the solvent plus water, because water is heavier, it will settle down, you separate that out, and the solvent again remains there. So this is by way of using non-polar solvent to remove water. This is done for example, all sorts of oils from oil seeds. The extraction is done to remove water. This is the way it is done. By Carl Fisher, it is a reagent in which you do the quick method. This is the most standard one. So the Carl Fisher reagent basically consists of iodine in pyridine, sulfur dioxide, and methanol. This method is the most potent method, but the only care that you have to take is that you can't use it for samples which have very high amount of water. Say for example, a material like syrups where 40-50% moisture, you cannot use Carl Fisher. There is a limitation of it, but this is a perfect method. Then refractive index. The Abbe refractometer is the equipment to know the refractive index. But what is refractive index? As I told you, when the light passes from one medium to another, suppose medium A and medium B, if the medium A is lighter, then the angle of fall on that medium, the angle of refraction in the heavier medium, it will go down. Like theta A will be higher, theta B will be lower, because theta, the medium, is denser. So refractive index of a substance is basically the ratio of speed of light in vacuum to the speed of light in the substance that we are checking. So how much is the speed of light in air or vacuum, and how much is the speed of light in the material which we are testing? That ratio of it is refractive index. So measurement using refractometer, so it is handheld refractometer, online refractometer, Abbe refractometer. The major applications is for quality control and for various other applications. I told you even moisture you can do it by refractive index. Refractive index applications are plenty. For example, ripeness of fruits, vegetables, sugarcane, beet. You can do it. Alcohol content in wine or beer, you can do it by refractive index. Amount of water present in honey. If somebody has put sugar syrup in honey, then you can do it by refractive index. Percentage of salt present in materials is possible by refractive index. Total solids present in the product, in any, like for example, coffee extract, chocolate, milk, baby food, you can do it by refractive index. Purity of liquids, how pure the vegetable oil is. For example, if there is adulteration of vegetable oil, then you can do it by refractive index. How do you measure the refractive index? Okay, refractive index is nothing but sign of angle of incidence made by a ray in air to the sine theta of refraction made by ray in the food sample. Say for example, this one. This theta A is the angle of incidence of light in air, and theta B is the angle of incidence of light in medium which you are measuring the refractive index of. So the ratio of sine theta A divided by sine theta B would be the refractive index. So refractive index measurement is very essential for various applications, from purity of liquids to amount of solids present, percentage of salt, amount of water in honey, alcohol content in wine, how ripe the fruits are, vegetable, sugarcane or beet. This all is refractive index can do this. You measure it ratio of sine of angle of incidence made by a ray in air. So sine theta in air divided by sine theta in the medium which you are, in the product which you are checking Ri of, is the simple formula. Now let us talk about filth. Filth is a term which is absolutely unacceptable, undesirable. And this is one factor because of which many of our products, consignments in Europe, failed several times. Now this has very number of definitions, but here I will talk about these filth which can be heavy, which can be light. What actually filth means? Filth is nothing but it is extraneous, which has come from outside, like sand, glass, iron, anything that is gone into the food which is not desirable. During production, during storage, or any decomposition of product on shelf, for example, food product is decomposing. So decomposition products are also filth. Filth can come from animals, for example, rodents, insects, bird matter, or due to unsanitary conditions. When the hygiene is not properly maintained, then there can be any sort of material ingressing into food. So that is filth. Filth can be heavy. Heavy means higher density. Filth can be light. Normally the high density filth settles down. For example, you take a solvent like chloroform. You put your food product in chloroform. The filth will settle down. All other material will dissolve in chloroform and you can separate it. There is light filth which is oleophilic. Oleophilic means it does not wet with water. So it is actually oil soluble filth. So this kind of filth you separate by putting the emulsion. So put the oil in water emulsion into the system. So the emulsion will float the lighter material and all others will remain there. After it is floated, you break the emulsion by adding alcohol and you sieve the filth, remove the filth by screening. You can also sieve the filth. If the filth is of bigger particle size, then you screen your material like any kind of liquid material or any juices, or if you screen it through the sieve, then all the filth will remain on the screen and the material will pass through. So this is, I was telling you about our Indian consignments rejected by Europeans, calling them filth just because of one reason, that they did not have proper label. They call the material as filth. So that can also be one way of, I think we have to be very careful what filth is. Here it is heavy, light, sieved, sieving of bigger particles, but the Europeans called our good product also as filth because on the label, not properly, everything was not properly written. So they called it filth. Then the next one is particle size, that is the diameter of particle size, diameter of particles which are there of the food. You do it by knowing the diameter, you do it by distribution of particles. This is something called sieve shaker. You see there are several types of sieves put, number of sieves, different particle size, and the bottom is actually container. So all that is which is falling through the sieves will be collected in the bottle and the machine will shake. So all the material on these sieves will be shaken, the finer will go down, the lighter will remain on the sieve. So you have a distribution of particle sizes of product done by this method. You can also do it by elutriation. Elutriation is nothing but you flow the liquid from bottom. So the heavier particles will go down, but the lighter will be with the flow of liquid will go up and separate it. So you can separate. Basically, this is for less than 200 mash, which is close to about minus 73 micron particle size. So you can, they will not be falling as the dense, as the bigger particle will fall. So they will flow along with the water and you can separate them. Last one is water activity. Water activity is about the equilibrium between the water, vapor pressure of water which is present in the product and the vapor pressure of the surrounding. Now, why it is important is because most of the products based on water activity, we increase their shelf life. For example, pickles. For example, various kinds of products which based on sugar. You must have seen in the market in sweets, for example. The products based on sugar and based on desi ghee will last longer because they control the water activity in such a manner that the microbial growth will not be there. So this is a very, very important term for the shelf life of products. Now in this chapter, what we have done, we have answered the question like what is filth, which is undesirable. What is the difference between heavy and light filth? Anything which will be hydrophobic, which will be oleophilic, will be lighter. Anything which is light in density is lighter. So it will float, which is heavy will sink. What are the techniques to remove, separate different types of filth? There are many techniques. The heavy will be just by gravity. The lighter will be use of emulsion. So put the emulsion, but emulsion should not have air in it. It should be free from air. The lighter filth will go up. While doing the moisture, it is always a challenge. Is another question why it is a challenge? Because removing the moisture from food products, it is absorbed, it is entrapped, it is adsorbed, is very difficult. If you want to remove all the moisture, maybe you end up giving more heat and damaging the product, which is not acceptable. What is the significance of specific gravity? We have already known that specific gravity is nothing but relative. It is relative to density of water. So density of the product divided by density of water. This tells you about whether material will float or sink, how much it will float, how much it will sink. Then there is a term called bulk density, which can be aerated, which can be compacted. Like in a sack of 200 liter, you can put maybe more of flour, but not more of grains. Grains you will be able to fill less, but the flour you will be able to fill more because the grains are aerated. Flour will not be aerated as much. So aerated and compact. What is the significance of bulk density? How much you will be able to pack? For example, you take chivda, you take mudi, and you have this roasted rice. So if rice in a sack, you may be able to put, for example, 50 kg. But in the same sack, if you have a roasted rice, you will not be able to fill more than maybe 15-20 kg. This is because of the bulk density. Carl Fisher reagent is used for actually moisture measurement. So this is again having iodine, pyridine, SO2, methanol together reagent, which is used for knowing the water content. Difference between water content and water activity. Water content is the moisture present. Water activity is to do with the vapor pressure, equilibrium between the water which is there in the product and the water, the vapor of the atmosphere. It has nothing to do with the content of amount of water present in it. Water activity is very, very critical. Surface tension is the tension at the surface because of the intermolecular forces keeping molecules binding together inside the media, and the rest, the on the top are forcing upward, making the top layer stretch. Surface of the liquid is stretched because of the surface tension. And what is the specific heat? It is the heat to increase 1 degree temperature of any product. How much heat is required? That is the specific heat. Thank you very much. Jai Ram Ji ki.